This is a review screen. So just I'm gonna pause a little bit, but I don't have time to go through again the review, and you will take a look at it for review. Okay, here I reviewed how to analyze earthquakes and how to catch variations. Now what is PGAs? Okay, I'm gonna pause right here. What is a frequency content, or what is dominant frequencies, and how we measure the frequency in hertz. Okay, and how we calculate all the frequency contents we have in the motions, contained in the motions, and come up with the dominant frequencies. Okay, this looks like a natural vibrations where we have many diverse combination of frequencies. And here, look at this. This looks like a machine vibrations, as I told you, and we only observe in one single very controlled vibrations. Okay. And this is a building on Earth, right? So when Earth moves due to the seismic actions, so actually the magma moves, the mantle fractures the crust, try to resist, and eventually moved all of a sudden, which will generate a inertial force on buildings. Do you follow me? So these buildings looks like very small. If you take a look at building, front of the building physically, then you think the building is huge structure that you can ever imagine in your vicinity, but actually it's not. Building is very small if you take a look at Earth's perspectives. Okay, so that building is very vulnerable to the action of seismicities. So we have to prepare well not to collapse the damages, not to collapse the buildings. Okay. And here we have a idealized mathematical model on paper. So we see a building as a cantilever, standing cantilever. Now we put earthquakes right there when we try to design the buildings, calculating stress and strain and displacement on the building. Fun, isn't it? Okay. This is what we're gonna do in tall building class, basically, and this is what engineers do out there when they design the buildings. So we are doing same things. We just start learning, but we're gonna end up with same purpose and same skill and same talents. Okay. Now let's take a look at what kind of dynamic properties we have to really consider when we take a look at the high-rise building behaviors. So first, very important factors that we need to understand in dynamic analysis is stiffness of the building, right? The stiffness is defined as how your building can resist against external loadings. So this is called a stiffness, and this is very stiff because this is steel box, steel lumps over there, and it's very difficult for you to create and cause any diffractions here, right? It is almost impossible because it's very stubby, chubby, fat, metal materials provide you almost infinite strength of stiffness is right there. Okay. And here you have a very flexible bamboo sitting on the top of ground, and it's easy to make this bamboo moving to the left, to the right, to there, in any directions. Okay, so this is said to have a very small stiffness and big flexibilities. Here, instead, you have very small stiffness, a very big stiffness, and very small flexibilities. Right? So what happens here? And when you vibrate, this is not right. Okay, I'm gonna have to delete this comment. Okay, I'm gonna have to delete this. So, and when you vibrate, you still can vibrate, even if you are having a infinite stiff materials. You can vibrate this, but it vibrates very fast. You understand? Why is that? Because when you have big stiffness, the vibration will go really fast. You can test at home, right? So if you vibrate one which has very high stiffness and very low stiffness, and the materials which has low stiffness will vibrate slowly. Okay, so this is what we can understand without introducing in mathematics. So in graduate school, we will study a mechanism of vibrations and stiffness, the stiffness versus flexibilities using some math, but not here. As I said, we don't use mathematics, but we just intuitively understand this phenomenon right here. Okay, now what is the first was stiffness, and second was a math. So math is a dimensionless quantity. So why the mass is calculated dividing weight by g. It's gravitational accelerations. So weight can change depending on your gravitational quantities. So your weight here in Earth are different from the weight at moon because your gravitational values are different, right? But if you divide W by G, then this value do not change anywhere in space, including Earth. So we try to carry the math. Okay, so don't forget the weight is not math. The math is obtained when you divide weight by gravitational accelerations. Okay, so this mass is also very important factor when you consider dynamic behavior of the structures. Right? So the how the mass is related with the vibrations is going to be explained very soon. Very soon. Okay, we learned this. The frequencies are inversely related with period. So simply divide inverse, and you can get one another, each other. Okay, and this is one of the very important clue that you don't want to forget for your future career as well. Not only just in the class, but also in the future career as well. So the frequency of the ground motions are very easy to understand right now as you learn how to calculate frequencies and period. The same thing for the buildings, right? So we have two frequencies between one in the building and one in the ground, right? So this also has a frequencies and the period, and also your ground motions has also frequencies and period. We call this period as a dominant period or dominant frequencies, whereas we see this as a building period and building frequencies. So we call this natural frequencies and natural period. We don't say natural right here. We say natural building period and building frequencies. You know why? And I'll explain that later as well. And here, the frequencies and period from earthquakes are referred as a dominant. The most earthquakes are having a dominant period and dominant frequencies. So these are one that affects the building behavior. And also building behavior will have their own natural frequencies and period. So don't get confused. We have one over here, we have one over here. Okay, now we're studying the period and frequencies of the building at these sections. Okay, and it is very difficult to calculate how many seconds do you need to make a one period. In other words, how to calculate period of the buildings, and this is very complicated. You need a very sophisticated software, structural software to calculate the building period or building frequencies, and you will calculate using Midas very easily, but you don't have to understand what's going on inside of Midas, but you will learn how to calculate building period using Midas. It is very straightforward if you follow my lecture on Thursday, right? And if you come to a graduate school, we'll calculate how to measure and how to obtain the natural period and frequencies of the building later. But that's one that in the graduate schools, okay? Right now, we have easiest a simple formula, even not go to the Midas. Even Midas, you need some input works, but this equation do not require anything else but just substitute some of the building information in this equation, which is right here. Okay, so t equal to 0.1 n, and the unit is second. And what it is to calculate your building period. Okay, and you say n, natural period. Right? So what is natural period? It is a period that represents your building vibrations, and it is how we just says natural. Natural means you don't apply any external loading to make the building vibrates. Okay, so we don't. How then can you make building vibrates without applying a loading? For example, you just pull it over by big rope and string, whatever, and then assume that you can cut it. Right? Then you can make this building vibrates. Right? This is how you vibrate to calculate natural period. And you don't need any applied load, but you need a initial diffractions and initial velocity. You don't have to know this right now. And this is what you're going to learn in graduate school. But anyway, you understand that when you measure natural period and natural vibrations, you don't apply external loading. You don't apply load. You just pull it up and you cut it. We call this ambient vibration test. Ambient vibration test. Okay. So if somebody asks you how you can make your building vibrate to calculate natural period, then you're going to probably say it using a ambient vibrations, and they'll understand what ambient vibration test means. They will recall this. All right. So here, using this formula, and what is n? N is a number of floors, number of stories of the buildings. So if you have 30-story buildings, n should be 30. If you have 10-story buildings, the n should be 10. Okay, and this is only good for a steel building. Okay. What if you have a concrete building? Concrete building, stiffer than steel building, as is. Steel building is flexible compared with the concrete buildings. So concrete buildings, as I explained right here, concrete building vibrates fast. In other words, natural period is smaller than that of steel, because it goes fast means it goes and to the right, left, and come to original position faster than that of steel buildings, which makes this Tn a little smaller than and this formula which is given for steel buildings. So we just try to reduce rationally how steel building 0.1 n times probably 8 times 80%. Or 80% come across as empirical. Empirical means experience. Empirical. And this is empirical formula either. So all this we check by the testing. We go on upstairs and measure each cycle using some measuring machines so that we make a statistics and finally come across with this formula for steel buildings and this buildings for concrete. So 80% for concrete with that of steel buildings. Understand? Clear? All right. So this is very simple. So you don't want to forget, not just in the class, but also in your work later, because this the equation is one of the most useful formula that I found myself in my work when I was working in a company. Okay, here. So if you have a 10-story building, if you here you go. I have a 80%, 90% is our building period for steels. And if you have a 10, 20, 30-story building, then what's the building period? Is just 3 seconds, right? What does 3 seconds means? 3 seconds means it's nothing but a time that takes to make one cycle. Is that right? This is buildings, and you go to right, go to left, you go to the original position, and you took 3 seconds, right? Or if you're having a 30-story buildings, okay? This is very amazing, right? If you want to calculate this using a minus, it'll take maybe a few days, maybe few weeks for those who start a minus learning at the same time. But it's just take less than 1 second and to get and come up with a 3 second when you have 30-story buildings using this formula. And if you have a concrete 30 building, concrete 30-story building, maybe 2.7, 2.4 second. Right? How accurate it is, I don't know. It is accurate based on the empirical experience. And empirical experience hardly disappoint you, which means this formula will bring pretty accurate solutions for you before you going into the Midas. So that Midas, this is very interesting. Actually, we have to go to Midas anyway to design buildings and all the diffractions, all those things. But you can check even Midas results of a period. If period is wrong, everything is going to be in vain. You don't want to use any output of Midas when the period is not right. And so you can check the period, whether the period is okay or not, based on this simple empirical formula. Does that make sense? So that if somebody spend 1 week and come up with a Midas period like 5 seconds, T equal 5 seconds for 30-story building, right? Then you will immediately recognize that your Midas model is something wrong with some error in code or whatever. Right? So how can you do that? You just simply use this empirical formulas, and this empirical formula will serve as a very convenient tool to check your computer model, Midas model, which can be very bad if they are wrong. Interesting. Okay. So We've been dealing with a lot of stuff today, so that I'll give you around 25 minutes to review the material that's been given to you today. And without understanding, it's gonna be difficult for your project in coming weeks. And if you understand, it'll be very fun for you to carry out the tall building projects with the Midas and everything will be okay. Okay. So thank you very much. Thank you very much for listening today. And I will continue to understand and take a look at the seismic aspects of high-rise buildings. Thank you very much.